Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. Tonight, I'll be doing the review for Quiz 5 and Quiz 6. How do you like those special effects, 5 and 6? All right, just to remind you, this Thursday, I'll be 8 o'clock a.m., the 31st of July. I'll be sending out 8 a.m. or earlier the passwords for Quiz 5 and Quiz 6. You'll have until Friday, 11:59, to hand upload your answers for Quiz 5 and 6. You need to upload each one as a single PDF file. And don't forget to be on time. If you don't follow instructions or are not on time, I reserve the right to subtract up to 25 points from either or both quizzes. All right, let me remind you, Quiz 5 has 4 pages, 9 problems, including some multiple part questions, but no multiple choice questions. It's worth 50 points. It covers Le Chatelier's chapter 15, chemical equilibrium, including collision theory of reactions, rate of reactions, chemical equilibrium, and I'll use my north side of Chicago French accent, Le Chatelier's principle, which is not how you pronounce his name properly in French. But that's my north side of Chicago accent. All right, Quiz 6 has 5 pages, 10 problems, including some multiple part questions, but no multiple choice. It's worth 50 points. It covers chapter 14, acids and bases. That includes Bronsted-Lowry acids, Bronsted-Lowry bases, chemical formulas of key acids and bases, conjugate acids and bases, water dissociation reaction, ionization constant of water, otherwise known as Kw, which is not named after me, even though I like to think so, and acidic, basic solutions, neutral solutions, pH determination calculation, buffers, and titrations. All right, let's go right into Quiz 5 review. Now, what you see on the screen, you can download the file cleverly named Chem 1211 Quiz 5 Review are these pages you'll see on the screen. And they're in the lecture folder of Blackboard. All right, let's go through it. First of all, collision theory. You should know molecules must collide in order for a reaction to occur. So that's why it's called a collision theory. In order to have a reaction, one, molecules have to collide. You should know that. Next, the colliding molecules have to have a certain amount of energy when they collide, and that's called the activation energy for a chemical reaction to occur. And colliding molecules for complex molecules have to have the proper orientation. It's like putting your key in the door. You have to have the key in the right way to fit in the lock. Same thing for molecules coming together. All right, now, when you do a chemical reaction, there's something called the reaction rate. That's the reaction, the rate is at which products are made or reactants are consumed. In other words, how fast are you making something? And that's an important parameter, especially in the chemical industry. Now, you should know factors that influence the reaction rate, the physical nature of the reactants. Solids react a lot slower than liquids, react a lot slower than gases. The concentration, how much of the reactants. And this is important. If you haven't figured out by now, when I put something in red, that's important. And that's a rule of thumb. Wait, it's on that thumb. And what does that mean, a rule of thumb? It's true 95% of the time. A law is true 100%. But this is an important rule of thumb, and that is the rate of a chemical reaction doubles for every 10 degrees C increase in the reaction temperature. So for most things, when you heat it up, they go quicker. Now, another important thing, which Dr. White used a lot in the chemical industry when I worked in it, are catalysts. And catalysts work by, you should know, lowering the activation energy to increase the reaction rate. Catalysts make something go faster by lowering the activation energy. And you should know how to draw energy diagrams for an exothermic reaction and endothermic reaction. Hold on while I open something up that's not open. All right, you should know how to draw energy diagrams. Let's look at the reaction. A plus B makes C plus D plus heat. This is exothermic reaction. How do I know it's exothermic? Because heat's given off on the product side. Heat is a product. Now the energy diagram, you have energy on the y-axis. And on the x-axis, we have time. At a starting point, A and B have a certain amount of energy. Now, there's a law in chemistry and science that you never create or destroy energy. And therefore, the total energy on the product side equal the total energy on the reactant side. Well, A and B have a certain amount of energy. Now, on the reactant side, some of the energy is lost as heat. Therefore, C and D have less energy than A and B, which is why it's lower. And how do you get from A and B to C to D? You go over the hill and down the hill. The grandmother's house, we go, well, not really, but, and something you should know, when you start at A and B, to the top of the mountain or hill is the activation energy, which I'll abbreviate EACT, subact. And you should know how to do this for an exothermic reaction. Let's look at an endothermic reaction. And here, Let's look at the reaction where you take heat plus E and F and you make G and H. This is an endothermic. Why? Because heat is on the reactant side. You have to add heat. Now, again, the total energy on the reactants is the same as the total energy of the products. On the y-axis, we still have energy. On the x-axis, we have time. E and F have a certain amount of energy. Now, notice the total energy on this side is E, F, and heat. Therefore, G and H will have more energy than E and F, because E and F have less energy than G and H, because G and H has all the energy of E and F plus this heat. So it's higher. And how do we go from E and F to G and H? You go over the hill and down the hill to grandmother's house we go. Not really, but it sounds cute. And again, from where you start to the top of the hill, this is called the activation energy, abbreviated E sub act. And you should know how to do that. Again, here's the exothermic reaction energy diagram. And remember, since heat is on the product side, the products have less energy than the reactants. On an endothermic, where you're adding heat, E and F have less energy than G and H, because you have to add also the energy to get it to equal to G and H. And again, both of these, from where you start to the top of the hill, is the activation energy. And know how to do this. Don't you love when I'm subtle? Oops, wrong thing. All right, next, and for quiz 5, we talk about chemical equilibrium, and that's a reversible reaction. An example of that would be A plus B, and you use the double-headed arrows, make C plus D. That means if you take A and B, you'll make C and D. If I make C and D, it'll make some A and B. Now, sometimes you'll also see the double-headed arrows like this. And that's the same thing. All right, now important thing about a chemical equilibrium. At equilibrium, the forward and reverse rate of reactions are the same. Again, you should know, at equilibrium, the forward and reverse rate of reactions are the same. The speed it goes one way and the speed it goes the other are the same. Now, it turns out, and this is a very important concept in chemistry, we have what's called the equilibrium constant, abbreviated E sub EQ. And for a chemical equilibrium, for this balanced equation, W moles of A react with X moles of B, remember the coefficient is moles, make Y moles of C, and Z moles of D. And the equilibrium is in brackets, that means moles per liter of C to the Y power, and you get the Y from the coefficient, times, not plus. Common mistake. Instead of this time, students put a plus. No, Don't do that. It's wrong. It's concentration of C to the Y power times concentration of D to the Z power divides the products divided by the concentration of each reactant to the power of the coefficient A to the power W times B to the power X. Now, when we have an equilibrium constant, the magnitude, how big it is, tells you an important thing about the equilibrium. How far to the products or the reactants does that equilibrium go? And the larger KEQ is, the more products are made. When KEQ is greater than 1, you make more products. When the equilibrium constant KEQ is less than 1, you make very few products. You have mostly starting material. Now, subtle time. And that's Le Chatelier's principle. An equilibrium shifts to the side to reduce stress put on the equilibrium. Now, I'm going to go through a problem or two from the problem set. You should know what happens when you change, like add or take away one of the products or starting materials. Which way does the equilibrium shift? You should also know exothermic reactions and endothermic reactions. One other thing I don't have on here, and this is ice bath removes heat. You should know an ice bath removes heat, and a hot water bath, sometimes saying put it in boiling water, adds heat. Ice bath removes heat, boiling water or hot water bath adds heat. And again, for each of the quizzes coming up, look at the practice problems. I'll say that again in slow motion. Do the practice problems to help you for quiz 5 and 6. Let's look at quiz 5, or chapter 14, practice problems, or 15, I'm sorry. Now, let's look at the following. For the following reaction, notice this is an equilibrium. What happens to the concentration of oxygen and chlorine if, let's look at A, add more water. At equilibrium, there's a certain amount of chlorine, certain amount of water, certain amount of HCl, and a certain amount of oxygen gas, O2. Now, what happens when you add more water? Well, now there's too much. And because of Le Chatelier's principle, the equilibrium says, oh no, I have too much water. I've got to get rid of some of it. Well, the only way it can get rid of it is water reacts with the chlorine to go this way. When something reacts, it's consumed and there's less of it. If you have 2 cookies and eat one of them, you have less cookies now because you only have one. Same thing when you react something, it's consumed, there's less. So when we react water with chlorine, the equilibrium shifts this way. What happens? You make more HCl and more oxygen gas, O2. So the amount of oxygen will increase. Now, if we look at this and we have chlorine, since we were reacting it with the water to get rid of the excess water, the chlorine is consumed. And just like if you have 2 cookies and you eat one, you only have one, you have less. When something is reacting, it's consumed, you have less, so the concentration goes down, it decreases. Now let's look at 10. If we take C6H6 plus hydrogen, H2, to make C6H12 plus heat, this is called the hydrogenation, which I've done reactions like this in industry. What happens to C6H6 concentration and C6H12 concentration, putting the reaction in an ice bath? And notice here I have the nice little note, ice bath removes heat, boiling water adds heat. So by putting it in an ice bath, we take away some of the heat. At equilibrium, there's a certain amount of C6H6, certain amount of H2, certain amount of C6H12, and a certain amount of heat. And by putting it in the ice bath, we've taken away some of the heat. And the equilibrium says, oh no, yeah, it does do this. Oh no, we need more heat. Somebody took some of the heat away. So how can it make more heat? Well, C6 and H6 react with hydrogen, H2, to make more C6H12 and more heat. So since you're reacting to C6H6, it's consumed, the amount will decrease. And since you're taking the C6H6 and the H2 to make more heat, you'll also make more C6H12, also known as cyclohexane. And therefore, you're making more of it, the amount will increase. Now, what happens to the reaction if you put it in boiling water? Boiling water adds heat. At equilibrium, there was a certain amount of C6H6, which is known as benzene, H2, hydrogen gas, C6H12, and heat. Now we put it in the boiling water, we've added heat. Boiling water or hot water adds heat. At equilibrium, there was a certain amount of heat. Now there's too much. We've added more and says, oh no, I have too much heat. I'm under stress. And how do you get rid of the excess heat? It reacts with C6H12 to make more, going the reverse way, C6H6 plus hydrogen gas. So what happens to C6H6 concentration? Well, if we're going to make more of it, it increases. If we're consuming the heat, To get rid of the excess heat, it reacts with the C6H12 that's consumed in this reaction. And when you consume something, the amount you have decreases. And you should know that. And that's quiz 5 from chapter 15. And these are the things you should know. All right. Let's talk about the review for quiz 6, which is chapter 14. The author has them in a bad way, and that's why I've reversed them. It makes more sense. All right, we're talking about acids and bases. These are things you should know. Hint, know this. What's a Bronsted-Lowry acid? It's a proton donor, anything that can give up a proton, H+. What's a Bronsted-Lowry base? It's anything that can accept the proton. It's a proton acceptor. Again, a proton is H+. Now, you should know the chemical formula for key acids and bases. HCl, hydrochloric acid. H2SO4, sulfuric acid. HNO3, nitric acid. One of the great miracles I personally think of life is in our stomach, we have cells that make HCl, which is why your stomach is acidic. It helps break down the food. And if you ever have taken Chem 1212 with me that I've taught at COD, that's organic chemistry, you learn about the reactions of HCl and water in your stomach to break down your major food groups. All right, but you should know HCl, H2SO4, and HNO3, nitric acid, are all acids. What are bases? NaOH, sodium hydroxide, KOH, potassium hydroxide, and ammonia. Now, one other base I don't have down here that you should know baking powder is essentially sodium bicarbonate. And you should know that. Now, it turns out water can react with itself, and it's in equilibrium. Two water molecules react to give the hydronium ion, H3O+, and the hydroxide, OH. But if you notice, the equilibrium is mostly to the left because the ionization constant, Kw, named after me, I wish it was in effect long before I was born, is hydronium ion concentration times hydroxide. And this really should be 1.0 times 10 to the minus 14. And this Kw is for water at 25 C, which is what we'll do in this class. But you should know this formula. All right, now, when we talk about solutions, and we're talking about water aqueous solutions now, they're terms acidic, basic, and neutral. An acidic solution, the hydronium ion concentration is greater than the hydroxide ion concentration, and that's acidic solution. basic solution. Just the opposite. The hydroxide ion concentration, OH minus, is greater than the hydronium ion concentration. And this is sometimes called an alkaline solution, which is true for your alkaline batteries. And finally, a neutral solution, the hydronium ion concentration is equal to the hydroxide ion concentration. Now, to think about this and say, well, what's this number and which is greater and which is smaller, and therefore it's acidic when H3O plus concentration greater than OH minus concentration, or basic greater OH minus greater than H3O concentration, H3O plus, or they're equal as neutral. That's difficult. And someone came up with the pH constant. And the pH scale is a number, small number, that's used to specify the molar hydronium ion concentration. And if anything I teach you this semester, acids and bases and pH are probably the most important. pH equal minus the log of the hydronium ion concentration. And my special gift to you is, if the hydronium ion concentration is 1.0 times 10 to the minus x, that's this right here, then the pH is x. If the hydronium ion concentration is this, then the pH is x. And you don't have to use logarithm on your calculator. That's my gift to you. Now, probably one of the most important things I'll ever teach you is the pH scale. It goes from 0 to 14. Under 7, it's acidic solution. At 7, it's neutral. And above 7, it's basic. Again, pH goes from 0 to 14. The lower the pH, below 7, the more acidic it is. The higher the pH, above 7, the more basic it is. That's the logarithmic scales. Now, I'm going to go through in a little while the couple key practice problems, but let's go on. You should know what a buffer is. A buffer is a solution that resists major changes in pH. This is important when small amounts of acid or base are added to it. A buffer solution is a solution that resists major changes in pH when small amounts of acid and base are added to it. If you add a dilute amount of acid or base, the pH doesn't change. By the way, your blood's buffered. Now, there's an important concept called titrations. And it's time for me to be subtle. Know this. At neutralization, when an acid and base react, it goes to neutral pH 7, and this is called neutralization. At that point, moles of acid equal moles of base. And to simplify it, I created this formula to help you out. Milliliters of acid times molarity of acid equals milliliters of base times molarity of base. And what you need to do is you'll be given 3 of these, and generally you'll either be asked to find the molarity of the acid or the molarity of the base. And this is an important concept, titrations, that's done many, many times in the United States, if not in the world, especially in the chemical industry, to determine when you're making something you do a titration, see how far along it is. All right, you should, for quiz 6, go through and know how to do the practice problems for chapter 14. Here I ask you what's the acid for Bronsted-Lowry base, a proton donor. What's a base under Bronsted-Lowry proton acceptor? You should know how to identify each of these as acid, base, salt. Hopefully you all know sodium chloride is a salt. All right, let's look at a couple of these. Number 4, if the pH, if a solution has hydronium ion concentration, H3O, equal 1.0 times 10 to the minus 3, what is the pH of the solution? And is it acidic, basic, or neutral? So we're trying to find a pH. We're given this. pH equal minus the log of the hydronium ion concentration. I give you that. When this is 1.0 times 10 to the minus x, pH is equal to x, so in this case 3. And here's the pH scale. Below 7 is acidic, 7 is neutral, above 7 is basic, 3, I hope you all agree, is less than 7, so it's acidic. All right, let's look at number 7. If a solution has the hydroxide OH minus concentration, the brackets mean moles per liter concentration, how much there is, of 1.0 times 10 to the minus 3, what is the pH of the solution, and is it acidic, basic, or neutral? Well, pH is minus the log of H3O plus concentration. Oh no, we don't have that. We have OH concentration. We're trying to find pH. So you need 2 steps. Those 2 steps. In step 1, you solve to determine what is the hydronium ion concentration, H3O plus. And remember, Kw, named after me, I wish, is hydronium times hydroxide concentration equal 1.0 times 10 to the minus 14. I want to solve for H3O plus, get rid of OH minus, so I divide by it. Whatever I divide by one side, I divide by the other. This cancels out. Here we have hydronium equals this over hydroxide. Put the number in, you get 1.0 times 10 to the minus 11. Are we done? No. We're trying to get pH. And we now have the hydronium ion concentration. pH is minus the log of the hydronium. We put this number in. When this is 1.0 times 10 to the minus x, the pH is x, in this case 11. Remember, when it's greater than 7, it's basic, less than 7, acidic, at 7, neutral. I hope you all agree 7 is 11 is greater than 7. It's basic. Here's some problems, 10, 11. I'll let you look on your own. You should know how to do those. All right, let's look at number 12. 10 points. And know how to do this. If you have to add 1.35 times 10 to the third milliliters of a 1.53 capital M NaOH solution to neutralize 1.87 times 10 squared milliliters of a HCl solution, what is the molarity of the HCl? So first of all, as soon as you see the new word neutralization, that means it's a titration. We're trying to find the molarity, capital M HCl, an acid. We're given the milliliters and the molarity of NaOH, a base. We're given the milliliters of the acid. At neutralization, moles of acid equal moles of base. That's milliliters of acid times molarity of acid equals milliliters of base times molarity of base. We want to solve for molarity of acid. To get rid of the milliliters of acid, we divide by it. Anything divided by itself becomes the number one. But whatever we do to one side, we do to the other. Divide by milliliters of acid. So now I rewrite it, molarity of acid equal milliliters of base times molarity of base divided by milliliters. Put it in there, 3 significant, 3, my answer is 3 significant, 11.0 times molar HCl, and you could have written it 1.10 times 10 to the 1 molar HCl. And I have some more neutralization problems. All right, remember, Thursday I'll be giving quiz 5 and quiz 6. And don't forget, do the practice problems, they'll help you. One other thing I didn't mention, for quiz 6, I have this sheet of important information. It's in the lecture section of Blackboard called Important Information Quiz 6. I didn't do it for quiz 5 because there are no real formulas you have to memorize. And this should be 1.0. And you should know these. And with that, I'm done for the evening. Wow, this was a busy evening. Don't forget, this Friday, I'll do a quick little important information about test 2 and the final exam and give you some hints on how to do the ACS final. Again, I'll put an announcement out today or tomorrow, Wednesday, about that. Don't forget, hand in your labs. And with that, I'm done. I'm going to say, gang gesund, go in health, and you know what I'm going to do now. Yep. Bye now. Bye now. Stole that from Granny to Beverly Hillbillies. Bye.